Thank you. Yes, I'm going to tell you where all the nuts are buried. So we have a projector.
You got it. There's a button.
Okay.
Oh, the button that can. Or didn't it? Yes. Come on.
There we go. Okay. Oh. There we go. Okay.
You can use the left arrow on the keyboard.
I don't want to have to turn around for every slide. Okay, it goes that way.
If you just use the left arrow, you can go back to the beginning and then the button there.
That one's not working either. There we go. Okay, so today I'm going to be talking about organic semiconductors and three major applications for them. This is really a new field, and the only application that you can actually buy right now are organic LED displays. But I'm going to talk about a couple other applications as well. So first I'm going to start off, maybe I do need the lightsaber. So first I'm going to start off, and for those of you who aren't familiar with the subject matter, I'm going to give you just some basic background information, some history, some of the chemistry that's involved with this, but I promise I won't go into too many gory details on the chemistry. And then I'm going to talk about three applications. Displays, this is what's been commercial for several years now, and it's about to boom as it goes into big screen TVs. OLED lighting, which is what we were working on at HP almost 20 years ago, and decided it wasn't ready for prime time. Maybe in another year or two it's actually going to be going commercial. And then a little farther out on the horizon is organic photovoltaics, solar cells made out of organic materials. It has the potential to be extremely low cost because it's essentially just a thin sheet of plastic that's your solar cell. And then I'm going to talk a little bit about some of the new manufacturing technology. You cannot use traditional semiconductor manufacturing equipment to do this. And then a few concluding comments. So what is an OLED? It's an organic light-emitting diode. The basic principle is just electroluminescence, the same as you have in any other light-emitting semiconductor. Silicon emits light in the infrared, so you can't see it. Gallium arsenide emits light that's almost visible. If you dope it a little bit, it becomes red. And of course, the high-power LEDs are based on gallium nitride. Those are blue emitters. And basically what it is you can have as little as one or as many as 100 layers of conductive organic materials, and then you have to have two contacts on either side. One of them has to be transparent to let the light come out. So it's an emissive display technology. So comparing it to LCDs, you don't need a backlight, you don't need color filters, you don't need the liquid crystal array. So the thing that's emitting the light is right out in the front of the display, and this is why they look so great. It has potential, and I want to concentrate on the word potential here, to be very cheap. Ultimately, possibly it's cheap enough to have disposable displays. Get a newspaper, unroll it, you get like a video screen of the news, you're done, let it roll up, throw it back in the recycling bin. That's a long ways off. Right now, they're less efficient and reliable than inorganic LEDs, but that hasn't slowed down their growth at all. So in the very, very simplest concept, this is what an OLED device structure looks like. You start with glass substrate. This is actually the thing you see on the front of your cell phone display is the glass substrate that it's all built on. Then you have a series of indium tin oxide lines that are put down for the front contact. This is transparent so the light can come through it. Then you can deposit, in the simplest case, it's just a single layer that does everything all in one layer. Then you have metallic cathode lines that are put down on the back side of the display. And because the cathodes are made out of metals that are highly reactive, this thing has to be hermetically sealed, which is one of the problems with the lifetime in these devices. So a little bit of history. This actually goes way back. The first observation of electroluminescence in organic materials was 1953. Anybody wants to follow up on these? These are the citations. The contact work functions, these are the metal contacts on polymer materials, 1960. In 65, we had double injection recombination. That means you have N-P type materials, not just a single layer. And in 75, long chain conductive polymer OLEDs were developed. And the first diode device was demonstrated. Again, this is an NP type structure by the Tang group at Kodak. This is kind of a sad story. Kodak originally developed some of this technology way back when. Their film manufacturing technology, which essentially is solution processing of large areas. Film has about 14 layers of different materials in it that could easily transfer to OLEDs. They actually had the first product on the market. The DSC EasyShare had an AMOLED display. But when they looked at the cost of tooling up to do this R&D, it was prohibitive. The research group that were doing that work, they tried to get funding to do a startup here in the U.S. Nobody was interested. They're all in China now. And conjugated polymers were developed by Burroughs at Cambridge, which spun off into Cambridge Display, which is one of the big companies in this area now. We actually looked at this at HP Labs and OED when I was back there in '92, but again, this is still true today. They're still not competitive with inorganic LEDs in terms of brightness and efficiency and lifetime. And the manufacturing cost is huge. So the first passive matrix OLED displays came on the market in 1999. In 2000, the Heger Group won a Nobel Prize for their work on these materials. And in 2005, the first active matrix OLED displays started shipping. And we think, actually it's quite likely, it may have happened already this year, that now active matrix OLEDs have surpassed passive matrix in terms of the shipments. So this is actually now a little more complex structure. This now shows you a two-layer device where you've got an emissive layer, which is also your electron transport material, and a specialized hole transport layer. In fact, this is still simpler than a real device. A real device would have multiple layers to inject the holes into the hole transport layer. You might have some barrier layers here, and you might have another actual electron transport separate layer and an electron injection layer. Now, this is not to scale, because underneath this you have this thin film transistor. This is what actually provides the power to drive all the pixels. If I try to do it to scale, this is many, many microns for the thin film transistor array, and this is maybe 100 nanometers for the whole OLED stack. So there are three different classes of chemistry that are used for OLEDs. One is called small molecules. These are typically fluorescent dyes or complexes of fluorescent materials in an organometallic compound. Compounds called dendrimers, which look like big, molecular-sized fuzzy tennis balls with thousands of different terminations on the outside that you can put different functional groups on to do different purposes. And this has, the dendrimers especially, besides OLEDs, you could use this as a drug and gene therapy delivery vehicle. You could make it soluble in certain body fluids and have it deliver a dose of something precisely where you wanted it. Then there's phosphorescent materials. These are good because they have an internal quantum efficiency that's almost 100%, whereas the fluorescent dyes are maybe 25 or 30%. So you get a 3 to 4x improvement in brightness with these things. There's a cost issue because they're organometallic complexes of iridium and platinum, very expensive materials. So these have very high cost, and nobody's been able to get a blue emitter with a long enough lifetime yet. Now, polymer materials, this is really the backbone of the OLED technology. There is almost an infinite number of custom molecules that you can design for any particular purpose you want. And as with the dendrimers, the side chains that you put on these terminations determine transport properties, solubility, and whatever you want, and the emission properties, what color, how bright, whatever you want. And these polymers are also the carriers for the small molecule and phosphorescent materials as well. So this is how you build one of these things up. You start with something simple, like a benzene ring. You react two of these together to make a double ring with this naphthalene. And then you bond two naphthalines together to get binaphthalene. And one of the important features of this is it's not just flat as it's shown in here, but in the 3D picture there's actually a 35.5 degree angle between these two naphthalines. And that's important. I'll get to that later. So now you can take this binaphthalene, and of course you make a polybinaphthalene, so it's hundreds of these in a very, very long chain. But I'm just going to show one here. And so now you can terminate these two positions. These are the two 2' positions with oxygen, which now makes it processable in certain types of solutions. Then you can go through another reactive step and stick a couple bromines on here, and this is now a whole transport layer material. But basically, depending on whatever you put on these terminations here, you can make a whole transport material, electron transport material, emissive material, whatever you want. So advantages of these binaphthalenes, like benzene, you can do the similar types of reactions, but the reaction conditions are much milder, so they're easier to control in a manufacturing process. Now, that large dihedral angle that I mentioned between the two naphthyl groups, it keeps the molecule from being closely packed together, and this has advantages. You have high efficiency and a low material density, too, which is important because this stuff's very expensive, so you want it to spread a long ways and cover a lot of area. And again, as I said, you can substitute anything on these terminations to achieve whatever properties you want from the material. And if you put something at the 2' positions, like I showed with the oxygens before, it actually opens that angle up even wider so that you have even a better effect. So some of the current and emerging OLED applications, well, right now, if you have a cell phone with a color display, it's an OLED display. If you bought it a few years ago, it was a passive matrix display. If you bought it this year, you've got a 50-50 chance, passive or active. If you buy it next year, probably 2 to 1 active. The advantages of OLED displays, they're brighter, they're faster, they have higher contrast, they have a wider color gamut, including at very, very low brightness levels, which is important for displays. No matter how dark it is, you have absolutely perfect color rendition and less energy use. So 3 new applications I think are going to dominate the future growth because, again, the growth is based on how much area of material you process. Doing little cell phone displays is not a high-volume manufacturing process, at least in terms of these. So large area OLED television displays, these are actually been shipping now for a year or two, though they're still outrageously expensive. OLED lighting, this is under development. There are a few companies now that are shipping samples, but you really can't buy commercial quantities of these products. And what's a little farther in the future, organic photovoltaics. There are a couple companies that are sampling things on this right now, but the performance is not where it needs to be. And again, the organic chemistry is the same for all of these as it is for the cell phone displays. However, the big problem right now, these large area applications are going to require large amounts of these very expensive OLED materials. If you're custom designing a very complex molecule, this stuff could be $2,000 a gram. So there's intense pressure to increase volume and reduce costs. And this is sort of the chicken and egg thing, right? Cost will go down if the volume goes up. Well, the volume will go up if the cost goes down. Who's first? So historical growth, this is what I was referring to just a moment ago. Again, 99 is when they started producing passive matrix. They actually peaked in 2006 and have gone down since the active matrix displays have come on. The active matrix displays are so much better looking than the old technology. This year, we're going to probably be 20 to 25% higher in active matrix. Samsung continues to dominate this business. They have over 50% of the market share for these displays. Again, these are mostly cell phone displays. A lot of other companies that you buy cell phones from, the displays were made by Samsung. And of all of these makers, Samsung, WiseChip, RIT, and Visionox, they're all either Taiwanese or Korean. Now, if you look out into the future, and I'm showing both the display and the lighting markets now. So again, displays, this year we're expecting something like about $4 billion revenue from the display business, growing to $23 billion in 2018 for a 39% annual growth rate. Pretty darn good. We have samples shipping. It doesn't even show on this chart yet, but in 2013, we expect to actually see these things on the market for the general public. And then those are expected to grow pretty dramatically too, but again, it'll take a while for them to catch up. Eventually, lighting will use more area than displays will. So, a little bit about OLED television displays. As I mentioned before, they have better color and contrast, a much faster refresh rate, that is nanoseconds instead of microseconds, and low power consumption compared to an LCD. Again, you don't have to make enough light to get through all those other things to see. It's right out in front of your face. So all of the major manufacturers are working on this right now. You can actually go, well, actually you can't. Sony released 17 and 25-inch professional monitors earlier this year, and these things are so hot, even though they're $31,000 each, they can't keep them on the shelf. They're sold out of their full capacity through the end of the year, probably longer than that now. These are used solely in the professional market. That is, most film production is done digitally now, so you look at your daily wraps on these, and you can go back and fix something if you have to. Commercials are very tight budget productions, and so you need to look at what you're doing, make sure it's going to look okay on the screen. But again, these are not commercial TVs. These are test instruments, and that's why the price is so high. For one thing, you can't have one dead pixel. The yield is very low when you're doing that. So LG had a 31-inch demo last year. They're going to release something over 50 inches in 2013. Samsung, 40-inch full HD in 2008. And Panasonic is planning to release 40-inch or larger, partnering with Sumitomo. And this is more of a gimmick. Mitsubishi has built 100-inch displays, but these are made up of small displays that are all tiled together to make a big one. That's cheating. And Seiko Epson is developing a 37-inch inkjet printable OLED TV. This is one of the new manufacturing technologies. And DuPont is really coming out ahead in a lot of this stuff. Last year, they announced they can make a 50-inch OLED TV in 2 minutes with a new printing technology, and they claim it has a 15-year lifetime. If that's true, then they've solved the lifetime issue. So this is some examples of DuPont displays and how they've kind of progressed. Boy, well, hopefully you can see that this one is kind of grainy and has some artifacts in it, stripes and things like that. This one's a little bit better. The colors are more saturated, but you can still see those artifacts. And in the 2008 versions, you can see it's completely free of those artifacts, and they're good-looking pictures. The problem is I can't really show you a picture of an improved brightness and color gamut OLED TV when it's projected through an LCD projector. So you have to actually go look at one. Look at the latest Samsung. That's an AMOLED display compared to the older cell phone displays, and see the difference in the color. So the larger displays require actually lower resolution. You have the same number of pixels in the display, but if the display is bigger, the pixels are farther apart, which makes it easier to fabricate them. And this kind of shows you basically the display resolution in pixels per inch versus the diagonal size of the display. Up here on the top, 4G, 5G, these are different generations of glass substrates that are used for manufacturing. 8G is the latest version, and the cost of building an 8G fab is over $2 billion now. So some interesting things. Your iPhone here has very, very high resolution, but it's a small display size. Apple has chosen not to go with active matrix OLEDs yet because they can't get the resolution on such a small display. Going way out here into the future, something you can look forward to is, well, we've got 55-inch and even 72-inch HD TVs now, but in a couple of years you're going to have a 55-inch 4K 2K. That means it's basically double the resolution, so it's like 4,000 pixels by 2,000 pixels. Those are going to be incredible. There are some difficulties with scaling up to these larger areas. It's common to all of these applications. It doesn't matter whether it's a display, a lighting, or a photovoltaic application. Besides the capital cost, these glass substrates at 8G, you're talking about 2.2 by 2.5 meter pieces of very, very thin glass, and you can get 4 55-inch displays out of one of these pieces of glass, and these are all processed individually. The glass has to be thin. They sag. And that means when you're trying to do a masking process and you're trying to basically put the mask against this thing and the glass sags away from it, So you get blurred images as you're trying to project through these things, and the fine patterns begin to blur. So you really can't go much bigger than 8G, and I don't know what a 9G fab would cost if you could even envision one. If you try to go to larger, of course, the glass is going to start breaking, and you're going to have yield losses when you start moving this from one step to the next. And like I said, 8G factory costs over $1 billion. Actually, the new ones that are being built, they're more like $2 billion today. It's just like a semiconductor fab, and it's the same type of equipment. We're still using the mentality that we adopted from the semiconductor industry, and you use the same kinds of fab equipment, the same kinds of thought processes for how you run your business. This is not going to work for OLEDs. It's going to have to change. Right now, there really isn't any manufacturing equipment infrastructure for these larger sizes. A lot of people are working on this right now, and I'll talk about just in a little bit more detail about some of those things later. But the key processes are solution processing instead of vacuum deposition processes. So instead of taking a big applied materials evaporator that you used to use to evaporate something onto your memory chips, now you're going to try to use the same equipment to evaporate organic molecules onto something. The equipment was not originally designed for that. It's a very high vacuum process. It's very wasteful of material. That is, when you evaporate, you have a point source or maybe a linear source if you're better, and this just gets hot and it sprays the stuff all over everywhere, and some of it gets on the thing you want it to get on. That if the stuff is costing $2,000 a gram, you do not want to throw 80% of it away and then have to clean it off later. So atmospheric inkjet printing. So instead of doing vacuum processing, now you can adopt another technology, which I like to say, hey, we did that work at HP too. Basically inkjet printing, but instead of printing ink, now you're printing organic polymers. And this is especially good for something like a very large diagonal HD TV display. So now you can print, you have separate nozzles for R, G, and B, and you can have multiple nozzles, so you're printing a whole bunch of these at once. And doing it at atmospheric pressure, essentially in air, you don't need pumps, you don't need vacuum chambers. It's a little harder to keep things clean, keep the dust off. But still, the cost is so much lower. And then finally, roll-to-roll processing. Basically, this is the same way newspapers are printed. If you can envision, heck, let's go crazy with this thing. Envision, say, a big roll of plastic sheet from here to the door and 10 kilometers long, all wound up on a big roll here. It's pulled off this roll, goes jetting through all of these inkjet printers and stuff like this at several meters per second, and coming out the other end, what do you have? You have an HD TV display coming out every few seconds. Oops. Yeah. Okay. Good. So here's one of the major problems right now that's specific to these kinds of solution processing and inkjet printing technologies. On this side, these are some solution processed large areas emitters, and the scale here has actually been kind of exaggerated so that you can actually see by eye what the differences are. Really, from brightest to dimmest, this is only going from like 100% to 80%, or in this case to 90% or 90%. So this is really a 10% maximum variation in light intensity over this whole area here. Your eye cannot detect that. In fact, it's very difficult for your eye to detect a factor of 2 change in light. Eyes are very logarithmic detectors. You can see very, very dim levels, and outside, well, if the sun were shining, very, very bright levels. So you can see there's patches here that depend on basically as you spray this solution that you then dry out over a large area. The spray is not the equal thickness everywhere that you put it. And so these add up from layer to layer to layer, and you get non-uniformities like this. But you can see there's no similar pattern to all of these. Each one is different. So every layer has its own non-uniformity, and that shows up in these. Now, when you're doing inkjet printing, everything has to be perfect, right? Each one of those nozzles from the inkjet printer has to be spitting out exactly the same amount of material every time you hit the hot wire. In this case, here is something that was manufactured, a green emitter, by the inkjet printing process. You can see these dark lines, we call them stitch lines. Actually, the Japanese have a term for it, it's called mura. This is one of the 3 types of waste, and it basically means unevenness. It's a term that's been adopted by the industry. But the variation between the bright pixels and the dark pixels here is really only about 7%. Normally, your eye would not be able to pick that up. But because there is a pattern to this, that is, it repeats with a regular structure, the eye is very, very sensitive to patterns, and you can pick that up, even though you might not detect the difference in 2 of them just next to each other, 2 large areas of 7% difference intensity. And what it turns out is the problem with this is one of the nozzles was clogged. Not completely clogged, just a little bit clogged, so it wasn't putting the same amount of material out with each spit. So now we're going to go, oops, I think, did I miss a slide? Oh, anyways, this is a good place to start. So now we're going to go into lighting. And now lighting is different from displays, okay? Displays are something you look at. And lighting is something that, we all know that lighting has emotional content to it. It has psychology to it. You have a certain feeling when you're sitting around a campfire. You have a different feeling if you're exploring a cave by flashlight. And this is a great example of this. This is in the Narrows. And this one little beam of sunlight's coming from 500 feet up. I think everybody, when you look at this picture, it gives you a certain feeling. Maybe not the same feeling for everyone, but it definitely gives you a certain feeling and maybe even a certain emotion if you've been in a place like this before. So in terms of technological progress, there's been a real rapid increase in the brightness and efficiency of these things. In 2007, you were maybe getting 35 lumens per watt. Today, it's over 100 lumens per watt. This is, though, from the actual emitter itself. By the time you package this thing in a module and put it in a luminaire that you hang on the ceiling or something, it drops somewhat. But comparatively speaking, 100 lumens per watt is pretty good. If you look at an incandescent 100-watt light bulb, 100 watts, 1,600 lumens, that's only 16 lumens per watt. Most of the energy that goes into your light bulb, 90% of it is turned into heat that just heats up your room. And if you're talking about big office buildings, all that heat from all those light bulbs causes much higher air conditioning requirements. So Philips and Osram are already shipping OLED products. These things are outrageously expensive. I'll get to some what the targets are for these things in a moment. But nobody is going to be buying these things except for your fictitious, extremely early adopter who has to have it at no cost because it just looks so cool. There's major effort underway in Europe right now. It's called Combo LED. They're trying to develop the cost-effective OLED lighting, but the real key is you have to have that supply chain infrastructure. This does not exist yet for OLEDs. The materials are in their infancy. There is no commercially available fab equipment for this stuff. All of this stuff has to come together to make it happen. So this is a 3-year R&D project. I believe they're supposed to be finishing up the end of next year, and we'll see what they come out with. It'll be interesting. So by 2015, many experts believe that 90% of all the area of organic LED materials will be produced for lighting applications. Again, displays are pretty small. Even if you look at big displays, it's still small. This display, hey, versus how many square meters of lights do we have in this room? And this is a huge display. And also solid state lighting, which means both LEDs and OLEDs, are going to dominate by 2025. The incandescents are likely to be phased out by 2015 and compact fluorescence by 2025. China manufactures most of the incandescent bulbs and probably 80% of the compact fluorescent bulbs in the world. And China's plans are to completely phase out the production probably by 2013. And one of the problems with CFLs are they have a luminous efficiency of probably 50 to 60 lumens per watt. So while that was better than the OLEDs were 4 years ago, the OLEDs are almost double that today. So again, just from an efficiency standpoint, you're going to want to convert all of your lighting eventually. And most people believe by 2025 you're not going to be able to buy either of these anymore. Another problem with the CFLs is, of course, they have mercury in them, right? Does anybody know how much mercury? 4 milligrams per bulb. And when you and there are billions of these manufactured. I think it was like 7 billion last year. And for each CFL bulb that you manufacture, there is, oops, we lost 1.6 milligrams of mercury into the environment somewhere. So not only do you pollute the environment with mercury when you're making these things, but then, so how many of you, when your CFL bulbs have worn out, have you gone through the full official procedure to recycle it so the mercury can be saved? No, most people just throw them in the trash, right? Just like a regular light bulb. So all of that stuff's going to get out into the environment. It's going to be a huge environmental problem someday if you depended on CFLs far into the future. So OLEDs are, for lighting, it's potentially a much simpler and cheaper process than that you use for displays because you don't have pixels, right? You don't have little tiny R, G, and B areas. But you do have to have R, G, and B emitters, but they can be either all mixed together in a single layer, or you can have stacked layers where you have an R, a G, and a B layer on top of each other, and the light all comes out together. So that's much, much simpler. You don't need the inkjet printers or anything like that. You just have to spray and bake one layer after another. Boom, boom, boom. So this is going to take a lot of material, though it's not as much as you think. I mentioned earlier that the OLED stack is maybe, typical number is 80 nanometers thick. So I did the calculation on this, depending, of course, on which polymer molecule you choose, but using that the naphthalene-based one, 24 kilograms of material would produce about 1 million square meters of either display or lighting or OPV, whatever you want. However, those 24 kilograms right now at, what, $2,000 a gram? It's not cheap. But if you get, economies of scale, mass manufacturing, if you can get the volume up by a factor of 1,000 or 10,000, which is going to happen, the cost will drop by a factor probably of about 20. So that actually brings them down now. $1,000 molecule turns into a $50 molecule. That's more than sufficient to meet the needs. So again, I mentioned LEDs and OLEDs are both considered solid state lighting. Of course, having worked at HP doing LED development for over 20 years, I'm very familiar with this process here. And again, historically, we've gone to more and more and more complex device structures to get the luminous efficiency up. The LEDs today, this is an old chart I stole from OSRAM. LEDs today, we have demonstrated in the lab almost 200 lumens per watt. And you can certainly buy products that have 100 lumens per watt. The typical stuff that you're going to get in, say, like Home Depot, where they got a little stand that shows all of their LED lights, those vary anywhere between 30 and 70 lumens per watt, depending on who makes them and how they're manufactured. One of the problems, of course, that limits the lifetime for LEDs is heat. You'll also feel it. They don't get as hot as a regular light bulb because you can actually put your hand on it and leave it there, but it's still pretty hot. Luckily, the LEDs, being an inorganic material, they can stand the heat. OLED materials being organic materials, they really cannot stand the heat. If the temperature of your OLED lighting panel rises by 20 degrees C, you're going to cut your lifetime by a factor of 10. So OLEDs have followed a similar track here. Again, as I was going through the history, remember you started with single layers, then 2 layers, PN junctions, then more complex structures where you separate the layers based on what the specific function is that you need to do. And this has actually been on a much faster curve than the LED industry has been. Part of this, though, of course, is the technology is more advanced than it was back here 20 years ago when we were doing this work. And you can take a lot of the learning from the LED industry and transfer it to the OLED industry, which is kind of why this is one of the reasons I'm working in this area now. And so it's rising very rapidly. We believe that if you just do the basic fundamental modeling, there's no reason why an OLED emitter and an LED emitter wouldn't have the same luminous efficiency. So at some point, probably 15, 20 years, these things are going to converge, and they'll both be about the same. So then you're just going to make your decision based on which is the cheaper technology. I'm betting on eventually, in terms of cost, if you can really get the high volume manufacturing, because they're made out of plastic instead of wafers that you have to grow. In the case of LEDs, almost all of the lighting today is based on gallium nitride that's deposited on sapphire wafers. Sapphire wafers aren't cheap. So if you do this on plastic or thin metal foil, it's going to be cheaper. Now this is again using that same semiconductor technology. The wet processing is nowhere, has not quite reached this level yet. Though actually, again, like I say, this is this is 2009. This is a 2-year-old slide. Where we are right now with wet process materials is probably 30 to 40. So up at this level, and these guys have risen to maybe 70. So again, the wet processing is catching up. But evaporation allows you to deposit those phosphorescent materials that have much higher quantum efficiency. So I'm not going to go over this in detail. This is the Department of Energy solid-state lighting roadmap. That is what they expect the industry to reach in terms of performance targets in the future. And I just want to concentrate on this here. This is the panel efficiency in lumens per watt again. So next year the target is 86. We think we're going to be able to meet that pretty easily. But then in 2015 the target's 125, and by 2020 it jumps to almost 170 lumens per watt. Remember, about 200 lumens per watt is kind of the theoretical maximum that you can do with these things. So that's a very, very aggressive number, and I'm not sure if we're going to be able to meet that. And of course, just look at the bottom line now. Again, you make the emitter, but by the time you put it in a module and put it into a lighting fixture, the efficiency is not the same, so it drops a little bit. And now I've just got some pictures of different OLED lighting panels that are being developed at different places. Fraunhofer Institute in Dresden is part of the European conglomerate that's developing the OLEDs, and they're demonstrating a quote-unquote 1 meter square OLED panel. The reason why this is made up of smaller tiles is because there are some problems with scaling these things up to larger areas. Displays that have active matrix, they have a little transistor that's driving every pixel, that's no problem because you have a whole backplane of transistors doing this. But here, for a lighting panel, you have to bring in the current along the edge with wires somewhere, in bus bars, and then the current has to be transmitted through the area through these organic materials, which do not have good conductivity and they do not have good carrier mobility. So there's a limit to how big you can make these things. Typically, they tend to be, say, 3 to 6 inches square. The other thing you might notice about this is, so here you have something that's equivalent to, maybe one of these luminaires up here. You'll notice these guys aren't lit up very brightly. Again, the efficiency is not that great for these things so far. But again, in very small sizes, it's much better. As you try to go bigger, and these guys are pushing the envelope here. When you get this size, I don't know if you can see it in this image, but they're a little bit brighter on the edges of each one. And that's because the current density is higher right near the bus bars. Here's another company that's making these, NovaLED. One of the features of the lighting is that you can make it on a transparent substrate, just like a cell phone display, glass. So this one's on a glass substrate, and you can see, even though the light is on, you can see her lips touching the backside of the piece of glass. So the possibilities here are you could make a window into a light too. You could see through it, whether the light's on or off. Of course, you can see through it better when the light's off. You could do the same thing with photovoltaics. You could have photovoltaics that are part of your windows. They extract some energy from the sunlight, but the rest of the light passes through to illuminate your room. Now, this is I think, the real future. Again, these cheap, flexible plastic or metal foil substrates. This shows one that can actually be bent. We were doing this back in the early 90s at HP. The trick about these things is, yes, you can bend them, but remember, they have to stay hermetically sealed to protect those volatile electrode materials. So if you bend it back and forth a few times, all of a sudden you've cracked the seal on the thing and they don't look so good. But that doesn't keep you from thinking of things that you can make a curved surface out of light where you don't keep bending it back and forth. And so these show some things that General Electric has been working on. This is roll-to-roll processed, about 10-inch square panels on plastic sheet. Here's where they printed stripes on the plastic sheet, and then they've done another one where they've wrapped this around to make a lighting fixture, or again, here's another lighting fixture that's kind of spiraled. And here's where they folded up a piece of green-emitting plastic to showcase. I had to put GE in there since I stole their picture too. Now here's some examples of OLED lighting. In this case, this is a private office. These are from Acuity Brands Lighting. Janine Fisher is one of their lighting designers there. And so they go with a design concept here that's basically sketched out by an artist, and then this is the realization with the OLED lighting. Notice how the whole room is nicely lit. It's kind of warm and inviting, as opposed to these very harsh luminaires that we have today. Again, these are, even though they're fluorescent tubes that are about an inch or so in diameter, it's still a linear line source, so it has very high brightness at the emitting surface. Whereas the OLED lighting panel has uniform brightness all over the whole thing. So when you look at it, the glare is not as bright. It's not as bright on a per unit area basis. And so you get much, not only do you get less glare in your light, but you have much more uniform light because it's coming from a larger area. Here's another example of a restaurant with OLED lighting in it. Again, the design concept. And here, this is actually, they did several design concepts, but this is the one that actually matched what they finally ended up doing here. So you've got color addressable RGB OLEDs up in here, so you can change the color of these columns. And then you've got the white OLEDs. Basically, these are, again, flexible plastic that's then bent into this shape. This is actually a thick plastic, so it's not something you can bend back and forth. Okay, organic photovoltaics. These are just emerging now. They're mainly in university and lab development. There are a couple companies, Canarca and Solarmer, that are commercially selling these things, but in very, very small volume. Last year at the Photovoltaic Specialist Conference in Honolulu, there were 72 papers on OPVs. This year in Seattle, now they upgraded us from emerging technologies to our own organic photovoltaic sessions. So I didn't count the papers. I think we're over 200 this year. Efficiencies have improved rapidly, though right now they're stuck around 6 or 7%. You need at least 10% efficiency, and this is why they're not taken off yet, to be commercially viable. And that's at a cost of $0.50 per watt. If you could actually get the efficiency up to 15%, then the dollar per watt target is viable. However, the cost of silicon panels keeps going down, so this dollar per watt target is a moving target. It could be very, very low cost, but just like I mentioned with the other technologies, displays and lighting, these contacts, when you put them outdoors now, high temperature extremes, rain, sun, all this other stuff, hailstones, they don't last very long. But if you can get this dollar per watt cost down, it's going to grow incredibly. But you've got to get the costs down as well. This is a very busy slide, and it's from NREL. It shows all the different kinds of photovoltaic technology and how they've improved in efficiency over the years. And I just want to show right down here is the organic PV. And the main thing I want to point out to you is look at how much the efficiency growth has accelerated in the last couple of years. More and more people are working on this. We have more and more critical mass. It's still not that competitive, so everybody's talking to everybody else, and things are moving a lot faster. So there's some new kinds of OLED manufacturing technology that'll take advantage of the characteristics of OLEDs. I mentioned solution processing using these custom designed molecules. You can do every layer except the final metal electrode layer, which still has to be vacuum deposited. It's a lot lower capital cost than a semiconductor processing tool is like $5 million up each and can easily approach $200 million. You get much better materials utilization, as I mentioned before, but again, the materials are very, very expensive. There's your 24 kilograms, 1 million square meters. You can print these things with inkjet printers. It's a big area for research right now. Very fast deposition speeds, up to 5 meters per second. Basically, you can make any size you want by just taking these inkjet printer heads and paralleling them up. The problem is the uniformity over large area. Remember the slide of the green Mura that I showed before. And then taking this one step further, doing this roll-to-roll processing on flexible substrates, you put all three of these things together, and now you have the basis for a new manufacturing infrastructure that we really need for OLEDs. So this is a very schematic example of roll-to-roll inkjet printing. I was thinking of putting pictures of the equipment there, but all it looks like is a big gray box with somebody's name on the outside, so it's not that exciting. So basically, you have your feed roll here, and that's feeding into now magnified view here. So you have, let's say you put down whole transport layer, then R pixels, G pixels, B pixels, and then electron transport layer, and then this all gets rolled up here, or maybe between two rollers, and it gets sheared off, and little displays keep dropping off the end of your production line. So now this is where I kind of bring it back to what is the relevance to computer science here of all this stuff I've been talking about for 40 minutes? Well, if you take a lot of these different things together, the tandem OLED device structures, that means stacking of layers, RGB like they were doing for lighting, development of organic thin film transistor arrays to replace the amorphous silicon arrays that they use in LCDs, and development of the equipment and materials. You're going to put all these things together. From the tandem work, you get higher layer count and the tunnel junctions that you need to separate different things. From the TFT arrays, you get improved mobility and speed. From the materials and equipment development, you bring all kinds of different functions and reduced cost. You need to get the purity up too. Put all these things together, and you can now envision making three-dimensional organic semiconductor arrays. These could be arrays of transistors. So like in a modern microprocessor chip, everything's in one layer. It's a planar structure. If you can imagine having a microprocessor transistor array, and then another one on top of that, and another one on top of that, and ad infinitum, maybe, and all of them interconnected. So now you have, instead of a planar network, a 3D network with many, many more connections between the different transistors. You don't know what you could end up doing with this stuff, but a couple things I'm thinking of. The easy things, well, you can make double-sided displays. You have two different things on both sides of the piece of plastic. 3D computers. Now you can have things that would start to resemble neural networks, brain connections. You can make different connections. They can be programmed to make their own connections the way the brain develops connections as it learns different things. The potential of this, I don't know where it could go. On the way over here, we were talking in the fact that you could use dendrimers to dose yourself with these things and have it start creating a microcomputer inside your brain. I don't know if I want to go there yet, but anything is possible. So, to finish up, I think the OLED industry is right on the edge of huge growth. These display sizes are going to go up, up, up. You're going to be getting this 55-inch OLED TV probably in 2 more years. And then the organic semiconductors are also going to be going into OLED lighting. Maybe you'll be able to buy these at a reasonable price in about 5 years. And OPV, kind of in the 5 to 7 year time frame, I think those are going to become big. They have several advantages over the existing technologies that are used for displays and lighting, but the big issue right now is the manufacturing cost. Organic PV, the efficiencies aren't where they need to be yet. If you could double them from where they are today and do it for under $1 a watt, you'd be home free. You'd be beating out everybody else, assuming you solve the reliability problem. And the improved materials and the development of this new manufacturing technology that I briefly described, this partially addresses this issue, but again, cost is tied to production volume. It's back to that chicken and egg problem again. But it will happen, just like it has happened with other technologies. So there's many other potential applications in other fields. It's a great place to be doing research and development work right now. Thank you for your attention, and I have a few minutes to entertain a few questions if there are any. 1 minute?
Yes.
Okay. Oh, boy, that was good timing. Yes.
You mentioned 4K, 2K displays.
Uh-huh.
I'm just curious your opinion of at what size of a display does 4K, 2K really matter?
Well,
Because I don't think that...
it depends on how close you sit to your TV, right? The pixel density is on the order in a standard HD TV, 55-inch. Pixel density is probably about 40 pixels per inch. So you would now go up to 80 pixels per inch, and I think even at a distance, you'll see a much, much sharper display. But also, just imagine now scaling that up to a 100-inch display with the same pixel density as you have in your 55-inch display now.
Well, thanks very much.
Hi.
I just wanted to say hi. I work at Agilent. I used to work at HP 32 years. So.
Hey, I like to say I worked at Agilent, at HP, Agilent and Lumileds. I worked
really?
in 3 different companies in 5 months, but I had the same phone number.
Oh, how funny. So, who do you work for now?
I saw the handwriting on the wall and took early retirement from Lumileds before
good.
things went crazy.
Good, good.
And so I'm a consultant now. I'm basically doing only what I like to do, which is
that's
predominantly photovoltaics. That's really what I'm after with
Yeah.
OLEDs, just photovoltaic
Oh, okay,
applications.
cool. All right, well, I just wanted to say hi.
Thank you. Hi, Hong Tao.
Good, good. Thank you. Yeah, so I just soon knew that I won't be able to join the lunch, but I'll be back to the meeting.
Okay.
Yeah.
I don't have an agenda for the meeting.
That's fine.
I've been burning the candle at both ends. Remember, I was supposed to be done by October, whatever that was, 22nd, and I've scheduled all these other things. And
Okay. Yeah.
well, now it's November 17th.
All right. Yeah. Okay. Yeah, I'll see you.
I'll just yank my thing out.
Yeah, probably, okay. It'll complain.
That's okay.
It'll get over it.
I've got it.
And it'll get over it.
This one I did too, but I think the way you do it,
I just want to get done. So I think the next hour.
Oh yeah, 1.08. Oh, right. And I think it's 1.13. I think that pink line is like maybe like 90% of it, you know? How frustrating is like there was a thing, it's fun. No, it's not fun. I think it like they had a jar of gumball and you had to get it some grain and yogurt and you wouldn't get it in the 25 bucks or whatever. Dead on. Dead on. I just wrote down the note. I looked at it and I'm like, oh, I don't know, but it's like 200 or something. And that's it. Like, you got it dead on. I'm like, can you receive and sell them like $4, size this up. Like some people can like figure it out. 1 gallon jar. So take a surface of that and look at my automatically. So like people don't rock I would much rather have gotten the gumball than have gotten the oh no, I do. Gumball though, like and I had to drive down there. I went there, got thrown out. I picked it up.
Ready went to Sarah.
All right, guys. So please put aside your notes. You only need a Scantron calculator. On the Scantron, make sure that you, if you change your answer, make sure that you erase it properly so that there's no misreading by the machine. If you're concerned that somehow you don't have the right type of pencils and your erasing is not successful, circle what answer you mean to leave on. Because as I said, I'm not regrading Scantron. So if somehow you don't get the right type of eraser or pencil and the erasing is not efficient, you can't then come back and say, well, I meant to answer this, but the machine read that. Because, it's hard for me to know whether the change was really done during the exam or afterwards. So in this case, if you look at your Scantron and you're like, well, that looks a little bit too gray to be discounted as a potential answer, circle for that question which answer you really meant, and then I'll check that the Scantron is read properly. Okay? And as usual, make sure that you, when you do some calculation, you show your work, and that you double check your answers before you break the exam. Show as much, as far as you can get with the calculation.
You're supposed to H, J, yeah.
For the future, I wrote row.
Okay, now, stop what you're doing. Before you jump into doing the multiple choice, there is one question that's on the test that I thought we would have time to cover, but we didn't go that far. So I'm going to write down for each version what the correct answer for that question is, because obviously it's not fair for me to assume that because it's something we haven't covered, but I thought a week ago that we would. Okay, so I'm going to write blue version question. That's the answer, and version yellow. So make sure you write that down. So basically, everybody's going to get correct answer on that. Yeah, Tyler.
On the practice exam, those questions, the ones that you told us to like cross out, that's not going to be on the test at all.
Well, actually, one is on, so that's why. Because a week ago I thought.
Right. Thank you.
So that's why, but the other ones are not.